Okay, we're live. All right, so measuring heat. So we measure heat with calorimetry or calorie metery. Okay, calor comes from Latin, means heat. Meter, it comes from Greek, it means measure. Language nerds hate things like that. They think you shouldn't combine Latin and Greek that way, but whatever. Calorimetry means measuring heat. Okay, this is where we get the word calorie. So we measure it with a thermometer. That's really all there is to it. This over here on the right, the big thing, complicated looking thing, that is a bomb calorimeter, constant volume. So you'll notice you have your reaction vessel here. That's where this is how we measure calories in food. We burn the food. Um, so you have your reaction vessel. You have your substance that you're burning. You have a wire so that you can ignite it. Then you have this steel envelope that won't change volume, and you burn your guy. Okay, it will release heat into its surroundings, and you measure the temperature change of the water. So here's your thermometer, and here is a thing that stirs the water so that the heat gets spread uniformly throughout the water. And so you measure the amount of temperature that the change in temperature of the water tells you how much energy was released by this reaction. Over here on the left, we have a slightly less fancy setup. This is a coffee cup calorimeter. Looks very, very similar, but this is a constant pressure thing. But you'll notice, once again, you have your water, you have the thing to stir the water, and you have a thermometer. And the reaction takes place inside the water. You're measuring the temperature change of the water. That tells you how much energy is released or absorbed by the reaction. That's really all there is to it. Calorimetry, I mean, you can get really expensive calorimeters, but that's because they're really good at controlling temperature and measuring heat exchange. All right. So the reaction heats the water, but heat is not the same thing as temperature. Remember, heat is the change in thermal energy. Temperature is the measure of the average random motion of the particles. So, but there is a relationship. Q is equal to mc delta T. Okay, so remember, Q is heat. M is the mass of a substance. C is known as the specific heat capacity of the substance, and delta T is the change in temperature. So you put heat into something, you're going to increase the temperature. How much the temperature changes depends on what the substance is. Some substances are really good at absorbing energy. Some substances are really bad at it. Okay, so for example, water has a very high specific heat capacity. You have to put in a lot of energy to change the temperature of water. Something like iron has a much lower specific heat capacity. It takes a lot less energy to change the temperature of iron. Okay? And then finally, mass. The more of the substance you have, the more energy you're going to have to put in to change the temperature. The less there is, the easier it is to change temperature. So you notice you pick up a penny off the ground, it feels cold at first. That's because your body temperature, your body heat is being used to warm that penny. But then you shift it over to your other hand, and it won't feel cold anymore. It'll be at the temperature of your body now. Because it didn't take very much energy, because it has a very small mass, and the copper and zinc in the penny have very low heat capacities. All right, so we're going to be doing a lot of different things with this. Okay, so specific heat capacity. Okay, the amount of energy measured in joules needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So that's why it's called a specific heat capacity. The specific means that we're talking about 1 gram of the substance. All right, so water, very high specific heat capacity, 4.184 joules per gram degree Celsius. Whereas you'll notice that iron, aluminum, and mercury are much, much lower, 0.45, 0.9, 0.14. So iron, it takes about 1/9 or 11% as much energy. Aluminum takes about 1/4 to 1/3. No, 1/4 to 1/5. Okay, So maybe 18%. Okay, mercury, it's way down there, something like 3%. Okay, it's just really easy to change temperature of 1 gram of mercury. I didn't go looking for this, but I found it in the Wikipedia page. Human flesh is about 3.5 joules per gram degree Celsius. That's because human flesh is mostly water. It's kind of gruesome, but I couldn't not include it once I saw it. Okay, so in order to change the temperature of 1 gram of water by 1 degree Celsius, you have to put in 4.184 joules of energy. Whereas for iron, in order to change the temperature of 1 gram of iron by 1 degree Celsius, you just need 0.45 joules. Okay, so that's what I mean when I say that water has a much higher specific heat capacity. And this, by the way, is responsible for different kinds of weather. Even here up in the hills of South Carolina, we're still really close to the ocean, and the ocean is made of water. So it is just a big old sponge that sucks up heat during the summer and then releases that heat during the winter. And thus, living on the coast, we have cooler summers because the ocean is sucking up that energy without changing temperature very much. And we also have warmer winters because then, having absorbed all that energy, the ocean then releases it. Whereas you go to the Midwest, far away from the ocean, they have much more brutal summers and much more brutal winters because they don't have that ameliorating effect. And then contrast that with England. England's a tiny little island, completely surrounded by water, and they experience very mild weather in England. I mean, it's very rainy, but it's still very mild, and it's because they're surrounded by that ocean. All right, so Q equals mc delta T. The more mass you have, the more energy it's going to take to change the temperature of the substance. Okay? A greater temperature change will also demand more heat, and a greater specific heat capacity will also demand more heat. Okay? So let's do some math. How much energy is released by a 125-gram ingot of iron? An ingot is just a chunk, just a little bar, with a heat capacity of 0.45 joules per gram degree Celsius, cooling from 450 degrees Celsius to 25 degrees Celsius. All right, so we bring up this guy. All right, so Q equals mc delta T. And in this case, I give the mass, 125 grams. I gave the specific heat, it's 0.45 joules per gram degree Celsius, and I gave the change in temperature. Final minus initial. We're cooling it down. So Q is 125.00 grams multiplied by the specific heat capacity, 0.450 joules per gram degree Celsius, times delta T. Final minus initial. We're cooling down to 25 degrees Celsius from 450 degrees Celsius. Okay. So final minus initial. Okay. Delta, that change always means final minus initial. All right. So that means that we're looking at 125 grams times 0.450 joules per gram degree Celsius times negative 425 degrees Celsius. Okay. This means that we're going to have a negative number for our heat, and that is what we should expect. It's cooling down. It's losing energy to its surroundings. Okay. So we bring up Mr. Calculator. 125 times 0.45 times, it's annoyingly difficult to put a negative sign there, so 23,906, negative 23900 joules, or negative 23.9 kilojoules. Okay. So it's releasing a fair amount of energy. That hot bar of iron, and cooling down from 450 degrees Celsius down to about room temperature, is releasing enough heat that if we could, perfectly harness it, it would be enough to lift 23,900 apples from the floor to the counter. All right, next problem. How much energy is needed to raise the temperature of 250 grams of water from freezing to boiling? Okay. So once again, Q equals mc delta T. And I gave you the mass. It's 250 grams of water. I gave you the specific heat capacity, 4.184. And I gave you the change in temperature. Okay, we're going from freezing to boiling. Okay, so Q is equal to 250 grams times the specific heat capacity of water, 4.184 joules per gram of degree Celsius. And our change in temperature, going from freezing to boiling, means 100 degrees Celsius minus 0 degrees Celsius. Okay. So we can plug all that into the calculator. 250 times 4.184 times 100 is going to give us, let's see, 4 sig figs, 104,600 joules, or 104.6 kilojoules of energy. Note that this is a lot more. So just going from 450 down to 25, the iron released 23,900 joules of energy, but going from just 0 to 100 took 4 times that much heat to change the temperature of the water, because water has a much higher specific heat capacity. Also, there was twice as much water. All right, next problem. What is the specific heat capacity of 12.278 grams of an unknown substance that decreases in temperature from 85 degrees Celsius to 25 degrees Celsius while releasing 210.028 joules of heat? Okay, so slightly different. Q equals mc delta T. I gave you Q, M, and delta T this time. So we're looking for the specific heat capacity. So C is equal to Q over M delta T. Okay? Just divide both sides by M, divide both sides by delta T. So our mass was 12.278 grams. Our change in temperature, 25.000 degrees Celsius minus 85.000 degrees Celsius. We started at 85, we ended at 25. And change in temperature means final minus initial. And it released, so negative 210.028 joules of heat. Okay. Remember, pay attention to your signs. Be careful about your signs. Releasing heat, okay, means that it is a negative quantity of heat. So now we can plug those into our calculator. 210.028 divided by 12.278 divided by 60. All right. So technically it's negative 210 divided by negative 60, but whatever. Your specific capacity better always be a positive number, or you've gotten an absurd response. Okay, if you have a negative heat capacity, that means your temperature would go down when you put heat in, and that's just weird and wrong. Okay, so this is going to have 5, this has 5, this has 6. Our answer has 5 sig figs. 0.28510 joules per gram degree Celsius. Okay, so that's a fairly low specific heat capacity. This is probably some kind of metal. I don't know what it is. I just made up all the numbers. I didn't base it on anything real. All right, now for a tricky problem. I'm going to need a full sheet for this one. Okay. What is the final temperature if you drop a 5-gram slug of lead at 85 degrees Celsius into 25 grams of water at 20 degrees Celsius? All right, so this is what we're looking at. Okay. Thing of water. We drop in a chunk of lead. The lead is at 85 degrees Celsius. Our water is at 25 degrees Celsius. Yes. No, it's 20 degrees Celsius. Excuse me, it's 20 grams. Yeah, 20 degrees Celsius. All right, what is the final temperature going to be? Well, the lead is warm, the water is cold. You're going to have heat moving from the lead into the water in order to warm the water up and cool the lead down. This exchange will continue until they're at the same temperature. Okay. Now, the reason you're able to solve this is because all of the heat going out of the lead is going into the water. All of the heat going into the water is coming from the lead, which means Q, the heat of the lead, is equal to negative Q of the water. Okay. All the heat going out of this guy is going into that guy. Equal in magnitude, opposite in sign. Okay. So it doesn't even really matter what the Q values are. All we need is M, C, and delta T. For lead is equal to negative MC delta T for the water. I'm just going to use H for the water. All right. So we know the mass and the specific heat capacity of both of these guys. We don't know the change in temperature, but we do know the initial temperature for both of them, and we know they'll end up at the same final temperature. So mass of the lead times the specific heat capacity of the lead, final temperature minus 85 degrees, because the lead starts at 85 degrees, is equal to negative mass of the water times the specific heat capacity of the water times the final temperature minus 20 degrees, because the water starts at 20 degrees. They both end up at the same final temperature. Okay. So we know this and this and this. We know this, this, and this. We're looking for our final temperature. Now, if you want, you can sit down and watch as I go through step by step. I'm going to just go ahead and replace this with the temperature of the lead, temperature of the water, to make it easier to write while I'm doing this. I'm going to go ahead and solve for the final temperature now. So I'm just going to go ahead and multiply through. So we get we just multiplied this guy times the final temperature and times the temperature of the lead. So MCTF, MCTP. Then we do the same thing over here. It's going to look slightly different because of this negative sign. Okay. Then the negative sign just means that these two swap positions. All right. So now we have a term with final temperature and a term with final temperature and two terms without. So I'm going to go ahead and I'm going to collect the final temperature stuff on one side and the other temperatures on the other side. So that means we add this MCTF to both sides, and we'll go ahead and add this as well. So basically all we're doing is swapping them. So MPCPTF plus MHCHTF equals MHCHTH plus MPCPTP. Okay, so this is the mass and the specific heat capacity for each of our substances multiplied by the final temperature. And this is the mass and specific heat capacity of the substances multiplied by the initial temperatures. But notice that they're different initial temperatures. Okay. And now we can do this. We just factor out the final temperature. Okay. And then we're going to divide both sides by this. And that will give us the final math problem, the final equation that we can use to solve for this. Okay. So the final temperature is going to be equal to this. There, now you can see it. Okay, so that is a big, complicated-looking equation. It's not really that bad. It kind of is. There's a lot of numbers going into this, but it's just it's basically saying that the final temperature is going to be an average somewhere in between these two temperatures. And how close it is and where that average sits is going to be based upon the mass of each of our substances and the specific heat capacities of our substances, as well as the two initial temperatures. Okay, so this is a version of an averaging sort of formula. So we plug in all of our numbers, and this is going to look weird, but so our final temperature is going to be the mass of the water. So that's 25 grams of water times the specific heat capacity of water is 4.184 joules per gram degree Celsius times the temperature of the water, which is 20 degrees Celsius. Okay. Plus, I don't have enough room, not when I'm writing with this Sharpie. The mass of the lead is 5 grams. The specific heat capacity of lead is 0.129 joules per gram degree Celsius. And the temperature of the lead, the initial temperature, I should say, 85.0 degrees Celsius. All divided by mass times specific heat, no temperature. So 25.000 grams times 4.184 joules per gram degree Celsius plus 5 grams times 0.129 joules per gram degree Celsius. All right. So keeping track of sig figs is going to be a real pain in the butt with this, but I'm going to go ahead and do that. I'm going to keep track of the significant figures on this one because I can. So let's go ahead, bring up the calculator, and 25 times 4.184 times 20, 2092. And we should have 4 sig figs. So that works out just fine. So 2092. And what units do we have here? Grams cancels, degrees Celsius cancels, so it's joules. Plus 5 times 0.129 times 85. 54.825. And we're going to have 3 sig figs, so 54.8 joules. And down the bottom, 25 times 4.184 is 104.6, and we're going to have 4 sig figs, and the units there are going to be joules per degree Celsius, plus 5 times 0.129, 0.645 joules per degree Celsius, and we're going to have 3 sig figs there. All right, so now we're changing operations. We're going from multiplication to addition, so the rules for our sig figs changes slightly. So 2092, oops, no, not 92, 2092. What the hell is going on? 2092 plus 54.8, 2146.8. But this one runs out at the ones, this runs out at the okay, so going to round at the ones, so 2147 joules up top, 104.6 plus 0.645, and that one runs out at the ones at that depth, so it's going to be 105.2 joules per degree Celsius. Now we do our division, 2147 divided by 105.2. Once again, we're changing from one kind to another. Our answer is going to have 4 sig figs. 20.41 degrees Celsius. All right. Does this answer make sense? That is really, really close to the initial temperature of the water. It's very, very far from the initial temperature of the lead. Okay. Does it make sense? Well, yes. Okay. Water has a much, much higher specific heat capacity than lead. 4.184 versus 0.129, it's like 40 times higher. So it takes 40 times as much energy to change an equivalent mass of water, the temperature of an equivalent mass of water. And it's not an equivalent mass of water, it's a lot more water versus the lead. Okay, it's 5 times as much water. Okay, so that means that it's going to be, 40 times the heat capacity and 5 times the temperature. The lead is going to see a 200-fold. It's going to change 200 times more than the water does. So yes, it makes perfect sense for the final temperature to be almost the same as the initial temperature of the water. Okay, and this lead wasn't very hot in the first place. I mean, 85 degrees Celsius, yeah, that's uncomfortably warm. I think that would burn you. But dropping 5 grams of warm, hot, uncomfortably hot, but not excessively hot lead into water, yeah, it does make sense for the final temperature to end up being very close to the initial temperature of the water. Water just has a very difficult time changing temperature like that because it is so good at storing energy. Okay? It has a very high specific heat capacity. All right, now we've been talking about specific heat capacity. We can also talk about molar heat capacity. So molar heat capacity is also a measure of heat capacity, but instead of grams, we use moles. Okay? So you can convert from one to the other very easily using the molar mass of your substance. So water has a specific heat capacity of 4.184 joules per gram degree Celsius. It has a molar mass of 18.01 grams per mole. So you multiply 4.184 times 18.01, and you get a molar heat capacity of 75.35 joules per mole degree Celsius. Iron, meanwhile, is 0.450 joules per gram degree Celsius and has a molar mass of 55.845 grams per mole, giving it a molar heat capacity of about 25 joules per mole degree Celsius. And now we can do the same sort of thing with mercury. Mercury has a specific heat capacity of 0.140 joules per gram degree Celsius, and it has a molar mass of 200.59 grams per mole. So we go ahead and we just gonna go ahead and bring up the calculator and do this math. 0.140 times 200.59 gives us a molar heat capacity of 28.083 joules per mole degree Celsius for our what am I thinking? For mercury. So that's really close to iron. That's not surprising to me. Most of our metals are going to have roughly the same molar heat capacity, somewhere around 25, just because there's only it's complicated. I'm not going to go into it, but water again is going to be much higher than our metals, just because it has so many ways of storing heat that just aren't available to the metals because they don't have molecules. Basically, that's what it comes down to. These guys, it's just individual atoms vibrating around inside the structure of the metal. But for water, the water molecule can rotate and it can vibrate, and there's a whole lot going on there that just isn't available to those metals. All right, so metals typically somewhere around 25. Okay, so what would it mean if a substance had a negative heat capacity? Like I said, if you get a negative heat capacity, you've done something wrong. Okay, it means that if you put energy in, the temperature goes down. And that's just not the way things work. So you're just not going to get a negative heat capacity. Get a negative heat capacity, go back and find out where you dropped your negative sign. Okay, you done screwed up. All right, so that is how we measure heat. Okay, we use calorimetry, we measure temperature, we measure mass, and we have to know the specific heat capacity. Q equals mc delta T. That is an equation you're going to work with a lot, a very lot. much of the time. Okay, so get used to that. Remember what it means. Remember what these three symbols stand for: mass, specific capacity, change in temperature. Remember, change means final minus initial, and then Q is energy measured in joules. All right. There's going to be more of that moving forward as we continue in Chapter 8. We're going to talk about calorimetry, standard states. We're going to get into enthalpies. There's going to be quite a lot moving forward. So let's go ahead. I'm going to do one last video tonight talking about calorimetry in a little bit more detail. So I will see you in a few minutes to talk about calorimetry.